How do we do these? This is just a little review. Do you remember how to simplify square roots? Yeah.
Are you trying to find a common factor?
Well, not exactly. You're trying to find the biggest perfect square. Yes, ma'am. Is that what you're gonna say? Okay, so what in this first one, what's the biggest perfect square factor of 125? 25. Okay, good. So what we're gonna take advantage of here with these, we're gonna take advantage of a property of square roots. Okay. We know this is the property we know. We know that the square root of a times b equals the square root of a times the square root of b. Okay? And if we can write this as the square root of 125, we can split that up into the square root of 25 times
The square root of
5. Good. Okay? 25 times 5. And we could even probably skip this step, but that's equal to the square root of 125 times the square root of 5, which equals, oh sorry, square root of 25, not 125. Whoops. Whoops, whoops. Which is equal to 5 squared is 5. Good. Good. And so our goal, whenever we're simplifying radicals, our goal is always just to get as much out of the radical as possible. That make sense? Okay. What about the one on the bottom? First of all, we always want to ask, can we simplify that fraction?
No.
Can't, can we? Okay, there's another property of radicals that's going on here. The square root of a over b equals what? Good, we can split it into separate square roots. Square root of a over square root of b. Okay, now there's one other little strangity here, or oddity that comes up. And this is kind of a weird thing. I don't think this is as big a deal anymore as it used to be. But to have a radical simplified, do you remember anything about the denominators? Do you remember anything particular that we always say about the denominators when we want to simplify a square root? Like, for example, is this okay to get an answer of 1 over the square root?
No.
It's not. What's wrong with that?
For some reason you just can't have those in the denominator.
Good. Okay, for some reason, and it's not even really a very good reason, but for some reason, for a radical to be fully simplified, we don't like to have radicals in the denominator. So we do what's called rationalizing the denominator. Do you remember what the trick is?
Yeah.
What is it?
Multiply it by itself.
Okay, you multiply the top and the bottom of the fraction by whatever the stranded radical is in the bottom. So in a case like this, we would just multiply the top and bottom by the square root of 2. And what would that give me on the bottom? 2. Good. So we get the answer. Oops. So we get the answer. How come I can't see that? There we go. So we get the answer square root of 2 over 2. Okay. So then what about down here? What are the steps we'd go through with this one? Okay, good. We're going to do kind of what we did up here for both of these, aren't we? So we get the square root of 8 over the square root of 125. Okay, let's get rid of this. And square root of 8, what's the biggest perfect square that goes into 8? 4. Okay, 4. So the square root of 8 we can split up into the square root of 4 times square root of 2. On the bottom, square root of 125 we already did. That's the square root of 25 times square root of 5, right? And so that simplifies at that point into 2 square root of 2 over 5 square root of 5. Okay, so let's rewrite that down here so we have a little more room. What do I still have to do here? What do you think, Cam?
You have to multiply the numerator and denominator with the square root of 5.
Good, okay, we gotta get that radical off the bottom. We have to rationalize the denominator, that's what we call that. And the reason we call it that is because the square root of 5 is an irrational number. If I wrote that as a decimal, it would just go forever, never repeat, never terminate, right? We can't write that as a fraction, another way of thinking about it. So if we multiply top and bottom, by the square root of 5, what's that gonna give us on the top?
2 square root of 10.
Good, good, because we can reverse, this relationship goes both ways, right? We can also combine two radicals into a single radical. So on the bottom we get, 2 times the square root of 10. On the top, sorry. On the bottom, what do we get? 5 times, what's all that stuff? Yeah, we get 5 times 5. It's 25. Okay? Good. Thus ends my review of square roots. There's a whole section on this, but that's it. It's as much as you guys need to see, probably.
The square root, I will multiply it into.
No. Okay, yeah, what about the 2? Good question. So, when we multiply this square root of 5, does it get distributed to the 2?
Yeah, does it ever, when you're multiplying out, does the top ever go to, a perfect number like 25? Instead of a-
Okay, good question. I suppose that's possible, but I don't think it will, as long as you have simplified this fraction initially. Doesn't seem to me, and I have to think about this a little bit more, like that's ever gonna happen. Okay, does that make sense? Because, and the reason I'm saying that, if this fraction is simplified, then the numerator and the denominator inside the radical don't share any common factors. And so I don't think that could happen. Somebody might prove me wrong, but I don't think that could happen. Good question though, yeah. If it did, if I'm wrong, and it does, you would do that though. You would, like if you got something in here like the square root of something that could be simplified, you would just simplify it. But I don't think that's gonna happen.
And I asked why, how does the 2 affected there?
Okay, the 2's not affected because I'm not distributing. I'm just multiplying 3 factors together. When I multiply 3 factors together, remember that multiplication is associative. So we can only multiply those in pairs, right? Does that make sense? That's an important point. Has everybody got that? So we wouldn't, what we've got is the square root of 2, we got 2 times the square root of 2 times the square root of 5. Now the most convenient order to multiply those in would be to multiply the square roots first and combine them into one single radical, which gives me the square root of 10. And then multiply that square root of 10 times 2, and those can't combine. Okay? And that's in the same way that 2 times 3 times 4 is 24, right? And not 2 times 3 times 2 times 4, 48, right? Does that make sense? Okay, so here's what I really wanted to talk about though. And I'll make this short and sweet. So I put everything away, put all distractions away. Okay, we talked yesterday about some strategies for solving quadratic equations, right? And what we looked at specifically yesterday were strategies where we could factor, where there wasn't a single x to isolate, right? We looked at stuff, I'll pick a real easy one. And this assignment, by the way, just real quick, I added another short assignment on rewriting quadratic expressions in general form or standard form, which just means simplifying. There's another one coming up, should be up today, about factoring. So the stuff we talked about yesterday, there will be an assignment that follows that. And remember, that's stuff like this. If we wanted to solve something like x squared minus x minus 12 equals 0, At this point, our only option is, because we haven't talked about other strategies, our only option here is to factor, right? Because I have multiple values, I have multiple instances of x that can't be combined, and so I can't isolate. Does that make sense? So we had to factor instead. But sometimes we can, and when we can isolate x, do it, because it's the easiest approach. So for example, what if we had a different equation like this? What if I had 2x squared minus 3 equals 11? Yes, ma'am.
On the top equation, can't you just do the negative b over 2a for it?
Negative b over,
Finding the vertex.
to find the vertex, to solve it, you mean? How are you gonna, I mean, you might be able to make that work. How would you make that work is what, I guess my question.
The b is 1,
Mhm.
the a is 1, so
Mhm.
negative, and then negative 1 over 2 times 1.
Okay, how's that helping you solve the equation? I mean, it's possible, and I thought you were gonna, I mean, you could potentially make that work. But and here's how, I don't, maybe this is what you were starting to think about. This is just gonna be a parabola that opens up, right? And so we're just trying to find where it crosses the x-axis. Does that make sense? And so it might be, so if we could do something like that, and we could find those intercepts, okay? But when you do that, essentially, you're still gonna end up doing the same algebra that we did yesterday, which is just factoring this thing, right? We could, real quick, we could break this up into what two factors? Remember, because x squared has a coefficient of 1, we know that the template, if it works, looks like that. And what would our magic numbers be here? Two numbers that multiply to negative 12, good, so negative and positive, and add to, so what would those be? Negative 4, positive 3, so our solutions then, I guess I probably should have worked all the way through this problem, so let's just move up here. So our solutions would be what then? X equals what? 4, positive 4, right? Or x equals negative 3, the zeros of those factors, okay? Now, what if we have an easier problem though? What if we have one like this? What's different about those two looks?
Solve for x.
Yes, there's only a single x there, isn't there? And as we said yesterday, if we can point to a single value of x, we can always isolate it, okay? So in fact, let's go ahead and skip over to the next page so we have a little more room. Okay, we isolate x, and you guys told me this yesterday. We isolate x by reversing order of operations, right? So we solve going in that direction. So what's our first step? Add 3. Good. So step 1, 2x squared equals 14. Okay, next step, good. Divide by 2, good. Okay, now, here's my question. Obviously, we know intuitively that the next step is to square root. How does that fall into our order of operations? Yeah, that's an exponent, right? We're undoing an exponent, okay? So, how does that work? What's step 3 gonna be then? Okay, so square root both sides, I heard people say, right? Square root both sides. Now, that gives us what on the left and what on the right? Okay, not quite. There's something we're missing there. Plus or minus. Yeah, plus or minus. What's the rule for that? If you remember, I mean, have you ever done, you've done this a little bit, right? If I square root both sides of an equation to solve for a variable, I always have to put a plus or minus there. Okay, we're going to get into this in much more detail later, but do you remember having talked about this? What happens if I cube root both sides? Do I need a plus or minus?
No.
You don't, okay? So can we make a general rule about that? What if I did a fourth root? Yes. So what's the trend? What's the rule?
Because it's gonna be opposite. Because it's, if you do,
Kind of.
because if you did like negative one.
Yes. Okay, if we're taking an even root of both sides, we have to have a plus or minus. If we're taking an odd root, we don't, right? Does that make sense? So we would have to have a plus or minus there. So I'm gonna show you why. And this is something that a lot of times people don't ever go through, but I'm gonna show you why. There's an important reason why that's the case. Here's the algebra behind that. Going from this step down to that step, there's a hidden step in there. So if x squared equals 7, what we're really doing is we are square rooting both sides. There is no plus or minus there yet. And a lot of books write this incorrectly. They'll put a plus or minus there, and that's wrong. All we've done is square root both sides. But now, what is the square root of x squared? Okay, it's not just x. That's what it seems like it would be. Now let's analyze this and see if we can determine what that function actually is. Let's try some sample values. So if we're gonna look into this function, we wanna know what is that guy? What is the square root of x squared? We're just gonna call it f of x for a second. Well, let's try, for example, f of 3. What value does it spit back? If I substitute 3 for x, I get the square root of 9. Square root of 9 is, and it's actually, okay, there's another, it's actually not. The square root of 9 is just 3. Okay, the square root of a number is just the positive or principal value. Okay, so the square root of 9 is just a plain old 3, no plus or minus. Okay, what?
Absolute value, 3.
Okay, now you're onto something. What if we put in a negative 3? What is negative 3 squared? 9. And the absolute value of 9, we already said, is positive 3. Now, what kind of function do we know that makes no changes to a number if it's positive, but changes it to its positive opposite if it's negative? Absolute value function is what does that, isn't it? Right? And so really, this is the definition of the absolute value of x. Okay? So what this is saying is the absolute value of x equals the square root of 7. Now, if we go back to our earlier review, solving absolute value equations, what did we always do when we had something like this, right? If we had the absolute value of ax plus b equals c, how did we rewrite that? Remember, we always had to trade an absolute value equation or inequality for two non-absolute value equations or inequalities. So what did this one get traded for? Ax plus b equals, okay, it equals c, or it equals negative c, right? Now ours is pretty easy. Ours, in our case, a is 1 and b is 0, right? But if we go back to our problem that we're working on, actually, a is, so ours is a little different. We didn't have any x's in there, did we? Sorry. But what would this equal then? If we solve this thing, no, there's our x. A is 1, b is 0. There we go. There. So x equals what? Either square root of 7 or x equals negative the square root of 7. Right? Say it again. Why is it only evens? It has to do with what that comes down to, and we'll talk a lot more about this later, but what that has to do with is the shape of an odd or even function. So if we look at, for example, I'll make this real quick, but it's a really good question. If we look at even functions, and let's just take an x squared for an example, but they all basically have this look. Right, so if we take an even function, y equals x squared. All even power functions have folding symmetry about the y-axis, they have reflective symmetry, right? Compare that to an odd power function, like x cubed. X cubed would just look like this. Right, that's y equals x cubed, okay? They have rotational symmetry about the origin, okay? Now, the square root of x is the inverse relation of x squared, right? So if I want to get a square root function, all I have to do is graph the inverse of the blue function. Remember how we did that? We either reflected it over the line y equals x, or we had a little trick that I showed you guys. We can just rotate 90 degrees counterclockwise and then rotate about and then reflect over the origin, or I mean over the line y-axis. And so it gives us this, right? We get, make sense? Okay. If we do the same thing for the purple function, we end up getting
So it makes
something like that.
So it makes it actually possible, more realistic, and like, so if it were cubes, you know how it's, if it were going this way, it's not possible, because you can't have it be like.
Right, exactly. So this is, so the kind of, I don't know what color that is, kind of the pink function here, that is the function y equals the cube root of x. See how that's defined for both positive and negative values of x? But the sideways parabola, that is the graph of the relation x equals y squared. If I solve that for y, don't I get back y equals plus or minus the square root of x? I have to split it into two separate functions because it violates the vertical line test. Does that make sense? So that's how it's going to be for all even functions. Okay, so even functions always are going to have this kind of a behavior when we look at an even root. And so they're not functions, they have to be broken apart into two separate relations if we want to treat those as functions, a plus or a minus. Whereas the cube root works everywhere. It's not finicky. It's a one-to-one function, meaning the purple function and the pink function, purple and pink relations are both functions, right? We know that the purple function's inverse is going to be a function and pass the vertical line test because the purple function passed the horizontal line test. That's a lot of information I just threw at you that we're going to review later, but there's an answer to your question, Julie. It's a good question. Yeah.
So this isn't really related, but what would
Okay, yeah, what would it look like? What happens when you start graphing overlapping even functions, here's kind of the trend. I'll exaggerate it a little bit. If that's x squared, then x to the fourth is just going to be more severe. And if I go like x to the sixth, it would even be more squared off and severe.
so like the bigger you get, the square?
The more square it looks, yeah.
What about like x to
Say it again.
the x to the fifth?
So x to the fifth, if I looked at those, say it's the same trend. So if I look at, like overlap the odd functions, if this is x cubed, this would be like x to the fifth or x to the seventh or something. It would just be more squared off, like that. Okay?
How would the parabola look like it? How would you write it? How would you write it and how would it look if you were using the three-dimensional?
It'd be a paraboloid. You would just spin it about an axis so it would look like a bullet or something. Yeah. Mm-hmm. Yep. Okay. So then we get for our answer plus or minus the square root of 7, right? So we can just, now I'm going to look at just one more example, and this is probably all we need. What would you do for one like this? What if we had 2 times the square root, I'll make as hard a one as I can, 3x minus 4 plus 5 equals 19. Okay, that's about the hardest one I can think of. If I wanted to, oh, sorry, that's not what I want to do. Darn it. It's got to be quadratic, not square root. So let me change that slightly. Different numbers so we can see. Okay. What are the steps in order I would go through to isolate x there? And let's rehearse them all before we actually do it. First I add 5, then I divide by 2, then I square root. Now, no, subtract 4, then divide by 3, right? So we got to work up, first outside of parentheses, we add, subtract, divide, multiply, exponent. Then we get to the parentheses and we just loop back again inside the parentheses and repeat the order of operations inside the parentheses. Make sense? So there's a lot of steps there, but they're not hard steps. So first, let's just go through those. So we get 2 times the quantity, 3x plus 4 squared equals, what, 34? Divide by 2, right? 3x, whoops, 32. Gosh, I'm blaming this on the cough medicine people. Divide by 2 and get 16. Okay. Square root, not 4, plus or minus 4. Good. So 3x plus 4 equals plus or minus 4. Okay, now I'm going to show you a good trick here. Now what?
So you x equals 0
Good, good. So I've got 2 different instances and I'm gonna add -4 to both of those, right? Okay, here's a good trick. If you, when you're adding or subtracting something to a side that already includes a plus or minus, so it's got 2 combined solutions already, put it right here in front of the plus or minus. Okay, so then we get 3x equals -4 plus or minus 4, and that gives you 2 cases, doesn't it? It gives you 0 or -8, right? But they're both included. And then the last step, divide by 3. And look what we get. If I divide both sides by 3, I get x equals -4 plus or minus 4 all over 3. Now I can go back all in one, just in one quick operation, and or 2 quick trials, instead of having to work simultaneously through 2 equations, one over here and one over here, I've got both my answers included. If we analyze this at the plus case, what do we get? 0 over 3 is 0, right? If I analyze the minus case, I get, Does that make sense, that little trick? Okay, so then you can still, it's efficient because you can still continue to do all your algebra as though it's one answer, but the plus or minus eventually is actually going to give you 2. Okay, make sense? All right, you guys are good to go. Let's. Oh, do we? All right. Well, why don't we just hang